In this lesson, we're going to learn all about graphs of polynomial functions. Now, the graphs of polynomial functions depend on two major factors that we're going to examine. What's called the end behavior of the graph and the location of its zeros. As we know, location of zeros are the same thing as x-intercepts, as long as they're real numbers, I should say. Okay, so let's talk about end behavior first. Now, if we examine graphs of basic even degree polynomials, you may notice that they all start from the positive infinity and end going toward positive infinity. For instance, let me show you. So y equals x squared, just a basic even degree polynomial. We know that it has a graph that's a parabola. So it starts, from positive infinity and it ends in positive infinity. Let's look at y equals x to the fourth power. It's not actually a whole lot different from y equals x squared. It still starts from the positive direction, ends in the positive direction, and the only big difference is it kind of just hangs around the x-axis a little bit longer at this 0. Okay? Similarly, x to the sixth power falls into the same pattern. Goes to starts from positive infinity, ends at positive infinity, and it's kind of squared off a little bit more right here at the x-axis where the 0 occurs. And if you do the 8th power, the 10th power, and so forth, this pattern still holds. Okay, if we look at graphs of odd degree polynomials, we'll notice that they all start negative and end positive. So for instance, y equals x. It starts from the negative infinity and ends at positive infinity. Y equals x cubed, same thing. It starts from negative infinity, ends at positive infinity. But instead of going right through the axis where the 0 is, it kind of hovers a little bit. It kind of takes its time passing through. X to the fifth, extremely similar. Starts from negative infinity, ends at positive infinity, and it kind of sticks around the x-axis a little bit longer at that 0 than x cubed does. Okay. Now this observation allows us to make the following general assumption about the end behavior of polynomials. If it's even degree, so you can write it as y equals a times x to the 2n power, so n could be any value. If you multiply it by 2, you're making it an even number. Now, if a is greater than 0, that's important because, if the leading term coefficient's positive, a parabola opens upward. If it's negative, it opens downward. But if the leading term coefficient's positive, then the graph is going to start from the positive direction and end in the positive direction. So the end behavior looks like this. Okay? So those dots represent anything can happen in between the infinities, but we'll take care of those in a minute. Right now, starts positive, ends positive. If a is less than 0, it's just the opposite. You start negative and end negative. So the end behavior of the graph will look like this. So I just tell people, think of a parabola and what it looks like, and use that as your basis for end behavior. All right, if it's an odd degree polynomial, and a is greater than 0, the graph will start negative and end positive. So just think of your basic cubic polynomial, y equals x cubed. The leading term coefficient is less than 0, it just flips. So you start from the positive direction and end in the negative direction. So that's your end behavior. And one thing I want to point out is with end behavior, We only consider the term with the highest degree because for large values of x, the other terms are very small in comparison and have no effect on the actual end behavior itself. All right, that's end behavior. Let's look at location of zeros. So if a zero of a polynomial is a real value, so if it's rational or irrational, rational of course means it could be written as a fraction or an integer. Irrational means it could be a square root. Then it is an x-intercept and is a place where the function intersects the x-axis. And I should say there's other ways of having an irrational value other than just square roots, but for our application right now, that's generally the way they're going to occur. So if I have a polynomial function in factored form, it's very easy to identify the zeros. And the zeros are if they're real numbers, these are the locations of where the graph is going to cross or touch the x-axis. So at -2, +1, and +3. And that's basically all you're doing with the zeros, just locating where on the x-axis your polynomial would pass through. When you couple that with end behavior, since this is an odd degree polynomial, there's 3 zeros, it should start in the negative and end in the positive. You can kind of fill in the details of what the graph should look like. Missed my arrow there a little bit. Pretty well. Okay, leading term coefficient was positive in this case, so I started in the negative, ended in the positive. One thing to mention before we move forward, though, is 0 is a multiplicity. So if a 0 is an x-intercept and a 0 of multiplicity, the graph behaves differently at that point. It behaves in a way similar to a polynomial of a degree that matches the multiplicity. So that sounds kind of strange. Let me show you what I mean. So for instance, most zeros are multiplicity 1. These zeros behave like lines and pass through the x-axis at these locations. So multiplicity 1, you just pass right through wherever your 0 is. Okay? However, if a 0 is multiplicity 2, the graph behaves like a parabola at this location. So the graph will touch the axis and bounce back away. So if it's multiplicity 2, it'll look more like a parabola at that particular point. And if a 0 is multiplicity 3, it behaves more like a cubic curve in that the graph will pass through the x-axis, but it will not pass straight through. It lingers a bit while passing through. So if it's multiplicity 3, it's going to look more like a cubic curve going through the x-axis. So let's see some examples here. So let's graph p of x equals 2x cubed plus 5x squared minus x minus 6, given that x equals 1 is a 0. Now, the reason I'm giving x equals 1 as an initial 0 is I want us to factor this, but if we use our process of factoring, the first thing that I'm going to do is get the calculator out, get a graph of the polynomial, and then get initial zeros. But if I'm looking at the graph, I could just copy it right off the screen. So I'm giving it initial 0 because I want to go through the factoring process for practice. So factoring out 1, so this would be 7, then positive 6, that's positive 6, and that's 0. And this is a quadratic, which looks like 2x squared plus 7x plus 6 equals 0. And let's see, 2x and x. Got to get this to 7. So I think, okay, if I do 2 here, that would be 4. 3 there, that would be 7. So positive 2, positive 3, So x equals negative 3 halves and x equals negative 2. So positive 1 is a 0. I'm going to plot that on my x-axis. Negative 2 is a 0. I'm going to plot that. And negative 3 halves. So that's like 1.5. So I'm going to plot that right there. Now, it's odd degree, and the leading term coefficient's positive. So that means I'm going to start in the negative direction and end in the positive direction. So just like a cubic graph. Okay, so let me draw our diagrams over here. So start in the negative, end in the positive. Okay, another thing that I know, which I can use, and it's not necessary, the negative 6 is my y-intercept, so I could actually plot that as well, just as an additional point to try and get, you know, as neat a graph as possible. And now I'm ready just to draw a graph through these points. So it's going to kind of go up like this through these, and then something like that, and there we go. Now, I don't actually know that this is the lowest point there, but I don't really have any reason to not know it. I actually don't know how high, whoops, I didn't mean to erase that, I meant to draw. I don't really know how high this peak should go as well. These are all questions that get answered in calculus. So for now, end behavior, location of zeros, that's all the most important things that we need to have demonstrated in our graph. So then let's look at another example. So p of x equals x plus 2 quantity squared times x minus 1 times x minus 3. Now this is in factored form just because it's easier to identify the zeros. So it's going to be negative 2, but it's multiplicity 2 because the square right here, it tells me that factor occurs twice, so that's a 0 of multiplicity. And then, whoops, don't need a parentheses, positive 1 and positive 3 are also zeros. So negative 2, positive 1, and positive 3. So there's a total of 4 zeros. That means my polynomial is degree 4. And it's even degree because it's degree 4, and a is greater than 0. So what that means is my end behavior is going to look kind of like a parabola. Okay, so like this. I'm going to start in the positive and end in the positive as well. Now, so starting in the positive, end in the positive. Now this 0 is multiplicity 2. And what's important about that is my graph's going to come down, touch the axis, and bounce back away. It's going to behave more like a parabola there. Here, it's multiplicity 1, so I just pass through like a line. Multiplicity 1, I just pass through like a line. So my graph, let me kind of draw it in one swoop here, is going to look more like something like this. Okay, so that 0 of multiplicity 2, I don't actually pass through the axis. I just come down, touch it, and then bounce back away. All right, here's another example. So my zeros, I've got negative 3, positive 1, but it's multiplicity 3, and positive 4. So negative 3, positive 1, and positive 4. So this is 1, 0, this is 3 more zeros, that's 4 total, and that's 5. So my degree is 5, which is odd. And if you'll notice, there's a negative out front here, so a is less than 0. So this is going to look like a cubic polynomial, but it's going to be flipped. So it's going to start in the positive and end down here in the negative. Okay, so now when I go to draw my graph, I know that I'm going to start in the positive direction, end in the negative direction. But one thing I have to be careful of is this 0 right here at positive 1, which is a 0 of multiplicity 3. So what's going to happen there is my graph is going to look more like a cubic polynomial as I pass through that particular 0. All right, so the others are multiplicity 1, so I just pass right through them as usual. So pass through here, come down, meet this graph, back up, and then like that. So just do your best to make sure it's very visible that your graph is, multiplicity 3 there. So it looks more like a cubic polynomial. All right, now another type of question might ask you to take a polynomial and figure out a function for it, which isn't all that difficult. The first thing you need to do is just identify zeros. So the zeros of this polynomial, we've got -4, +1, and +3. And I pass through the axis for each one of these, so that means my graph is always multiplicity 1. Each of those zeros is multiplicity 1. So if I write this in factored form, I could write p of x equals some constant, we'll take care of that in a minute, times x plus 4 times x minus 1 times x minus 3. All right, and that is a pretty good polynomial that contains this graph. The only thing that might be off is this coefficient here. All right, it could be positive, could be negative. If you'll notice, I have a third degree polynomial because I have 3 zeros, starting in the positive and I'm ending in the negative, which is the opposite of what you usually do. So my leading term coefficient should at least be negative. Okay, and one thing that I just noticed, this particular point right here is actually at -60 and not at +60, so we'll need to take that into account in just a second. So if I set my polynomial up this way, just putting in a constant for a, I can solve for it pretty easily if I know some point that exists on the graph. So for instance, I know that the point -2, -60 exists on my graph. So this means x equals -2 and y equals -60. So I can set, get the right, -60 equals a times, and if I plug in -2 for x, it would be -2 plus 4 times -2 minus 1 times -2 minus 3. So -60 equals a times 2 times -3 times -5. So -60 equals a times 2 times -3 is -6. -6 times -5 is +30. So if I divide both sides by 30, I get a is equal to -2, which means my polynomial p of x is now equal to -2 times x plus 4 times x minus 1 times x minus 3. And just leave that in factored form. You certainly could multiply it out to a, third degree expanded polynomial, but it's not necessary. This shows me everything that you need to know. In the homework, the problems there only want the answer in factored form as well. Let's try one more of those. All right, find a polynomial in factored form that has the following graph. All right, so zeros. We have -3, 1, and 4. So let's write those down. -3, 1, but there's something different about 1. Notice the graph comes up, touches the x-axis, and bounces back away. That's multiplicity 2. And 4. All right, so what that means is my polynomial initially looks like some constant times x plus 3 times x minus 1, and to take care of the multiplicity 2, I just put a square on that, and x minus 4. Now, I have an initial point to work with right here. So x and y values I'm going to plug in. So we'll say -10 equals a times -1 plus 3, -1 minus 1 squared, -1 minus 4. So -10 equals a times 2, this would be 4, and -5. So 2 times 4 is 8. 8 times -5 is -40. So if I divide both sides by -40, I get a is equal to 1/4. So that means my polynomial in factored form is 1/4 x plus 3 times x minus 1 quantity squared times x minus 4. Okay, this last example we're going to do, it's something that we've done already, but just to reiterate how to do this process, approximating zeros on a calculator. So the first thing you're going to do is whichever polynomial you're given, you're going to graph the polynomial. Then use the zero function to calculate the location of these zeros. Make sure not to use just the trace feature or just moving the cursor around because it's not accurate enough. Make sure you press the second, calc, and use the zero function. So the polynomial I'm going to use here is x cubed plus 8x squared minus 2x minus 1. And let's just walk through finding the zeros here. So I've got it plugged in here, x cubed plus 8x squared plus 2x minus 1. And I'm going to hit zoom and 6 to make sure I'm in the standard viewing window. And there are my zeros. So the first one I notice is over here. It's definitely not passing on an integer, so we need to calculate where that's occurring. So let's do second in calc and 0. Now it wants a left bound, right bound, and initial guess. So my left bound, I'll say -9. My right bound I'll give as -5. And the guess, say -7. And then it calculates it, and there's my 0. Now, in your homework, you'll be asked to round to the nearest 10th or round to the nearest 100th. Whatever you're asked to do, just follow those instructions. I'm just going to round to the nearest 100th here. Okay, so that's one of my zeros, but it looks like I have two others. In order to get those, I'm going to zoom in on them, though. So I'm going to hit zoom, get zoom box, and just move my cursor around to about right there, and really zoom in on this region right here. Okay, so those are the remaining two zeros. It's a third degree polynomial, so I know there's 3 of them. Clearly they're not on an integer, so I need to calculate where they are. So my left bound, I think I'll use -1 as the left bound, 0 as the right bound. The initial guess, I'll put -0.5 in. So it's close to that, but not quite. It's -0.52 in this case, rounded to the nearest hundredth. And then my last 0, second calc 0, my left bound I will use 0, my right bound I'll use is 1, not 11. There we go. And my initial guess I'll just put in as 0.5. And then it calculated that right there, and it is 0.25 if I round to 2 decimal places, because the 7 rounds the 4 up. So just remember, if you're approximating any zeros, make sure not to use the trace feature. It seems like it would work. You know, for instance, if I hit trace, move my cursor around, seems like it would work, but it doesn't always land directly on a 0. Let me bring it over here and show you this one. So it gets pretty close to where that 0 is, but not exactly.